To all of you who are joining us, welcome. We're going to spend just a couple of minutes and let everybody come on in, and then we'll get started. So why don't we start? It's a great pleasure to welcome all of you to this latest iteration of our research symposium that highlight the great work that some of our colleagues in some of our faculty in the Department of Mechanical and Industrial Engineering here at the U of T do. My name is Marcus Bussman. I'm the privileged to be the chair of our Department of Mechanical and Industrial Engineering, and it's a great pleasure today to welcome you to a talk on a very timely topic, given what is happening in Ontario at the moment. So it's a privilege to introduce you to Professor Dionne Aleman. So Dionne is an associate professor here in our department and the director of the Medical Operations Research Lab. She is a professor on the industrial engineering side of MIE and holds appointments to a number of other places here at the U of T, including an Institute for Health Policy Management and Evaluation, a U of T Institute for Pandemics, and an appointment to the TECNA Institute at UHN at the University Health Network. Her research focuses on the application of OR, or operations research, to medical systems and healthcare systems to improve quality, timeliness, and efficiency. And over the past year, if you've been watching the news, you have occasionally seen Dionne kind of in the media talking about her work applying her expertise to pandemic modeling. With regard to our students, she teaches a number of popular courses, and as well, a past number of years has been our coordinator for the industrial engineering capstone projects that all of our fourth year students are involved with. And so with that, I'm gonna well, hang on, before I do that, I'm gonna let her take over in just a second, but just a few words of logistics. So I think Dionne's going to present for 30 or 40 minutes, something like that, and then we'll do a Q&A afterwards. But in the meantime, if questions occur to you that you might want to have answered afterwards, there is a Q&A button at the bottom of your Zoom screen. You can feel free to drop questions into that Q&A at any time. We'll collect those, and then I will moderate a little session afterwards to get Dionne to answer a few of those. The other thing I want to mention is that as per the email that went out and the invitation you got, this we'll run this until no later than 1 p.m. Toronto time. And then if you'd like to continue the conversation with Professor Aleman and others, we have a link to another app called GatherTown. And I would recommend, if you can, that you try to enter that using Google Chrome. But that's an app that really allows us to have a little more of an informal networking session where you can spend some time and talk to others, including us here. So I encourage you to come to that. We'll provide more details at the end of this session on how to hop over there. So without further ado, I welcome Professor Aleman and let her take this over.
All right, thank you, Professor Bussman, for that lovely introduction. So before I get started, and in case you've forgotten, because we've all been remote for so long, here is our lovely university campus, University College in the background, and that's this direction. That's our building, mechanical engineering building, just hidden so delicately behind all of these leafy trees. Clearly summer was in full swing when this picture was taken, and looking forward to summer again and to seeing campus again. So like Professor Bussman said, I'm sure you all know why we've been remote for so long, and that's because of COVID-19. So I'm here today to present to you some of the work that I've been doing in helping one of our provinces model COVID and plan appropriate responses to it. So first and foremost, a little bit how we model the spread of disease in general. So the most common approaches that you see to modeling the spread of disease are what are called compartmental models. So if you've heard the terms SIR, SEIR, these are compartmental models, where the S stands for susceptible, I for infected, R for removed, And optionally, there can be an E for exposed. Right, so some of these models can have a lot more types of categories of individuals and groups of different population members, but generally this is the main thrust, SIR and SEIR. And these are the models that you will mostly see presented by governments, by public health units, as they try to predict what's going to happen with disease spread in the future. So these models are really quite high level. They take in just a few bits of high level information. So the first is R0, which you probably know by now is what's called the reproduction number. This reproduction number says how many infections will one infected person cause. So if R0 is greater than 1, that means that each infected person sort of sets off a chain of geometric growth of the disease, and that's how we get that exponential disease spread. But if R0 is less than 1, then each infected person doesn't fully replace themselves in the population of infected people, and so the disease will just die itself out all by itself. These models also generally involve looking at, say, contact rates, the average number of contacts that a person has, as well as the recovery rate. So how quickly or how long does it take for somebody who's been infected to recover? Okay. Now, when I first started getting into modeling disease spread, which was actually just before H1N1, maybe over 10 years ago, I looked at these models, and just the general principle of them, to me as an engineer, seemed to really kind of miss the mark of what's actually important to capture in a system of a population and a disease spreading through it. The thing about these high-level models is that because they're very high level, you can't really assess nuanced policies without a priori assumption on policy effects. So for example, if you wanted to assess the impact of, let's say, closing businesses, you'd have to make an assumption about how that changes people's contact rate. And then on top of that, R0 is an average number, right? So obviously every person who becomes infected is not going to infect, let's say 2.4 additional people. So that's kind of in the range of what COVID-19 is thought to be. Some people will infect a lot more. Some people will infect maybe 0. And same thing with contact rates and recovery rates. Some people will have a lot more contacts, some people less, some people recover faster, some people recover slower. So there are a lot of heterogeneities that are involved in a real population that just get averaged away by these compartmental models. So as an engineer, I thought we have to do better. Definitely we can and should do better. And so I started getting into the world of agent-based simulation models, which are abbreviated ABS or ABM, depending on where you want to put the acronym. Now, as it turns out, the more I became involved in pandemic planning and the more I learned about pandemic models and how they're used by public officials, I came to realize that compartmental models are actually really very important. So as much as I sort of said, oh, these models are so problematic, later I learned they're actually hugely important and play a very important role in public planning, particularly in the event of an emergent disease like COVID-19, where not that much is really known about the nuance of how diseases spread. So if not a lot of information is available, these compartmental models are basically our primary tool, because like I said, they only require high-level info to go into it. Of course, only high-level info goes in, so only high-level information comes out, and then that's where we have this issue of not being able to really model the types of real-world policies that are put into place. But again, these compartmental models give us quick population trends, very good generalizations about what's going to happen overall, and they really play an important role in planning for a pandemic. Now, occupying a different space and a different role in modeling and planning is agent-based models. So with agent-based models, what we have is essentially just a ton of individual agents, okay, in this case, people just running around, going about their daily lives. They'll have contact with some people that might increase their chances of being infected, which then might have them change their behaviors. Maybe they go to a hospital, maybe they end up in ICU, maybe they recover, maybe they don't. And maybe they just choose to do certain behaviors based on the people around them. Okay, so with an agent-based model, we can really model kind of anything that goes into the model, right? If we know about where people live and where they're working, we can do a lot of workplace analysis. If we know about the schools that they're in, we can do a lot of school analysis. If we know something about comorbidity prevalence in different, let's say, census subdivisions, we can build those comorbidities statistically into our individual agents and then assess how different communities might more or less be impacted in severity by outbreaks. Now, of course, the challenge here is that these models require just an absolute metric ton of data, right? So anything that we want to analyze, we have to collect data about it in order to model it. And that can take a really long time because data is just kind of all over the place. And then there's really only one or two commercial softwares that can do a decent job with agent-based simulation models. And if you want to do anything with very large populations, you kind of can't really go with the commercial software because they just can't handle, they don't scale up very well. So you kind of have to code up your own if you want to do something very large and very fast, which in itself is a challenge. And then there are computational challenges like needing lots of RAM, lots of CPU power in order to do lots of simulations in a reasonable amount of time. So that's how I came to develop what we call morPOP, the Medical Operations Research Lab Pandemic Outbreak Planner. So it's a seasonal continuous time simulation implemented in C++. And by continuous time, I mean that we update the model in a fixed time step, in our case, every day in the model. We update people's probabilities of becoming infected, whether or not they actually transitioned to becoming infected or recovered or died, as well as making other behavioral changes, implementing policies like school closures or business closures. All of that happens on a day-by-day basis. So this model, we actually started building it way back in the day. Okay, so cue old-timey silent movie music. So we actually built this model just as H1N1 hit, which was really very coincidental. We started it slightly before H1N1. And we built this model in collaboration with a senior researcher at what was then called the Ontario Agency for Health Protection and Promotion, now called Public Health Ontario. And we use this to model the Greater Toronto Area, which has 6 million people. Therefore, our model had 6 million agents. So this was among the largest agent-based models presented anywhere, and also among the most detailed, and also it was able to run very fast. And because it's a computer program, the disease is just defined by a bunch of numbers and probabilities, and the population is just defined again by a bunch of information from StatsCan or wherever else. We can easily extend this model to other locations and diseases just by changing the input files. So we have a bunch of things going on in the model, right? So we have our people, and we have tons of information about these people, where they live, where they work, are they commuting, comorbidities. We make assumptions about their behavioral probabilities, as well as including out-of-province travelers that can come in and stay for a certain amount of time and then leave. People interact in a lot of your typical environments: household, workplaces, schools, hospitals, etc. And then also, in addition to those sort of fixed environments, people just have kind of incidental random community contacts every day, like crossing people on the street or in a store, things like that. For a disease, just like we can be as detailed as we want about our people, we can be as detailed as we want about our disease. So here's some of the properties that we take into account for our disease. So transmission rate per minute per age group, death rate adjusted by comorbidities, latent period. So that's the period where you're infected before you have symptoms. So how long is that period? How many days are you contagious after that latent period? When you're pre-symptomatic, or let's say asymptomatic, if you never develop symptoms, which is actually really quite common with COVID, how contagious are you compared to somebody who's fully symptomatic, right? So we can have that distinction built in, and we can also play around with what percent of infections are fully asymptomatic. People's behaviors, pretty much exactly what you would expect in real life. And then we've assessed a number of public policies that I'll talk about here in this presentation. So just a quick note on including contact tracing. I think it's important to discuss that contact tracing is actually incredibly difficult to model, right? You basically require just a ton of memory, having to store for everybody how many contacts and with whom they've had over a previous duration of time. You can't just have these sort of averaged, homogeneously mixed environments that most commonly define compartmental models. And that's why when you see models presented by governments, or like we're probably going to see some models being presented later today by Ontario, these models don't include these standard public health measures to mitigate the spread of disease, like contact tracing or anything else, because they're really, really difficult to model. So when you see those projections, you always have to bear in mind that these are 99% of the time projections of what would happen if we don't do anything. Okay, so these projections are often essentially a call to action. Like, if we don't do anything, we might see, let's say either like this high level of exponential growth, or maybe like some low level or somewhere in the middle. But they don't take into account something like contact tracing, right? Even as limited as it's been in Ontario, it is still something that's present and effective. And so when the actual number of infections tends to, undershoot the projections, people then think that the models were totally off base. In fact, we can't truly know if they were totally off base, because we always do something. And of course, if we do something, it's going to be better than doing nothing. So always keep that in mind when you're seeing models presented. So what happens in our model, so similar to compartmental models, but on an individual level, is that people fall into an SIR category, and also D for dead. So people start off being susceptible, which means healthy and essentially eligible to become infected. And they can either stay susceptible from day to day, or they might become infected. And once somebody's infected, based on their age and properties about the disease, we know how long they'll stay infected, after which they'll either become recovered or they'll become dead. And if somebody recovers, then from day to day, they stay recovered. That's where they are. They're absorbed into that state. Same thing with being dead. So really, the only piece of information here that we actually need to know is what's the probability that a susceptible person becomes infected from one day to the next. And we calculate that probability based on each person's exposure to infected people. So if person J is exposed to infected person I for some amount of time with a particular disease transmission probability on that day, based on their age group or different properties about this pair of people, I and J, we can calculate their exposure. And then it's just a very simple statistical reduction after that to figure out the probability that person J is infected at all, right? So we just take the probability that person J is not infected by person I, and then the probability that person J transitions from S to I is just 1 minus all of those probabilities. So it's really quite simple. We've also recently updated the model to include these sort of environmental, what I call fudge factors, but they're basically risk factors that have been produced by the Vancouver School of Economic Risk Factors, specifically for COVID-19. They've done huge studies in every province to assess, based on your particular environment, like let's say a home, or like an airline pilot or a factory worker, what is your additional, like above average risk of becoming infected. And so we incorporate those into the model based on the environments in which two people have contact. So I've been working with Newfoundland and Labrador on this COVID modeling project. So a little bit about Newfoundland and Labrador. They're an Atlantic province, so here's what they look like. Labrador is the mainland part. It's mostly rural, and then Newfoundland is the island part that is home to their capital, St. John's. The province has a little over 500,000 people. They had their first COVID case March 14th of last year, and they had 0 active cases for almost all of the time since their first outbreak, well, until quite recently. But up until recently, they had a total of 262 deaths, with almost all of them coming from one outbreak at a funeral home that was in fact caused by a traveler coming in for a funeral. So that's something to think about. So Newfoundland was in a really great place up until early February, when they had a huge outbreak, again sparked by something travel related. But as you can see, they were very quickly able to get this outbreak under control by very quickly responding with quite a number of public health measures, short shutdowns, contact tracing, et cetera. And now they're back into a position of very low to no community spread. Just for comparison, here's Ontario, and you can see, no doubt about it, here we are in the third wave. Hospital occupancy is starting to creep up, ICU occupancy as well, and this red line here at 300 is what the Ontario health experts say is the sort of catastrophic point of no return in terms of ICU occupancy, after which we're going to have very serious problems delivering healthcare to the general population. So you can see Ontario's in really quite a very precarious position right now. So just a little bit of analysis on just these curves. My colleague on this work, Randy Giffen from IBM Canada, has done some work just doing some simple curve fitting and matching. He's able to looks like predict pretty accurately what will happen with hospital occupancy with an offset of 8 days. So meaning hospital occupancy, we might expect it to start changing 8 days after whatever's happening with cases. Similar thing with ICU capacity, ICU occupancy. You see it's going up with a lag of 15 days. And deaths, maybe this curve isn't fitted so well. And of course, this number is kind of really rapidly dynamically changing as more and more vulnerable populations get vaccinated. But we can see that deaths, seem to be lagging behind actual cases by 20 days. So that's something interesting. Okay, so some actual model results. So first, I'd like to just talk about a little bit of structure of the models. So these are results from last year. We've made just a ton of changes and updates and added a whole lot of new features since then. But one thing that we observed last year that was interesting is that if we simulated out a full year, which by the way is not something that we do for predictive purposes because so much can change over the course of the year, even over a couple of months. Normally we confine our simulations to, like, let's say 3 or maybe 4 months at a time. One thing we can see is, so the blue areas are when school is in session in the model. We can see that these curves really are very highly correlated to when school is in session, which probably should not actually be a surprise to anyone. Put a bunch of people in a confined space. Of course, there's an opportunity for disease spread, even if kids, as it seems, tend to be much more likely to be symptomatic or have very mild, asymptomatic or have very mild symptoms. In these results, schools are homogeneously mixed. So it's important to note because we didn't have a lot of data about the individual schools themselves. But one thing that we found is that when we had community contacts being homogeneously mixed, or what we call aggregated, so if you're in a group of a community of 100 people and one person in that population is infected, you would essentially have kind of like a 1% chance, downward adjusted with some probabilities of becoming infected the next day, right? So everybody's just kind of in a big pot mixing together. So if any one person is infected, there's a chance that everybody could become infected. And that's generally how compartmental models operate. But when we actually went down to doing exact one-to-one contact, so basically we picked, a bunch of pairs of people and say, you guys are having contact. What we found is that our predicted numbers actually fell a pretty significant amount. Now, much more recently, after lots of changes and updates and new features being added into the model, we got exact information about schools and their classroom sizes in every grade. And once we built that into the model, we'd see that our predicted number of infections again really drops. Okay, and then once we add exact community contacts on top of that, we see again just a huge reduction. So the observation here is not so much that models that have homogeneous mixing are inherently flawed or are always going to significantly overpredict, but it does seem that there is the ability for them to overpredict if they're not really very carefully tuned with the mindset of everybody being mixed together and everybody having just this baseline probability day to day is not actually accurate. These models do have to be carefully tuned, so it's just something to keep in mind. But also, really the purpose in doing these models is not so much to pay attention to what's going on the y-axis, right? It's much more so to capture how effective are certain policies at reducing our predictions. Okay, so for example, if here, so exact schools and exact contacts is our baseline prediction, how effective is adding contact tracing? Right? How effective is adding Newfoundland's school closure policy on top of that? And we can see that these two policies are very effective at bringing down this curve from where it is here. Now, how effective is having a school closure policy on top of contact tracing? Well, it's a little bit difficult to see here. I could zoom in, but instead, maybe we'll look at the impact on contact tracing of having a school closure policy. And with the detailed ABS, we can actually pull things apart, like, how likely is it that that there's going to be a daily call load of, let's say, 500 people that have to be contacted for contact tracing versus 1,000, et cetera, in order for the province to help plan how much capacity do they need for contact tracing, or how much is one policy likely going to help them from getting behind schedule on contact tracing. Then we can also do a lot of analysis on unknown parameters. So, we're over a year into COVID and still so much is not well understood about this disease, which, as an engineer just drives me crazy, but that's medicine. That's just how it is. So things are not always as cut and dried as they are in our nicely packaged world of engineering and math. So first thing that we looked at here is the pre-symptomatic contagiousness discount. So for example, if you're pre-symptomatic, are you 100% as contagious as a symptomatic person, or let's say 75% as contagious as a symptomatic person, right? All the way down to 0%. And unsurprisingly, okay, we can see that if a pre-symptomatic person is just as contagious as a fully symptomatic person, we're in a bad place, right? Because pre-symptomatic people don't know that they should be staying home, don't know that maybe they should seek medical treatment. So there's at least, let's say, 5 days of a latent period where they're just out and about doing whatever. And how much does that matter? A lot, right? How important is it to get a handle on what this number is? It's pretty important. Although, once we get down to saying like maybe only half as percent or half as contagious as a symptomatic person, okay, we could say that that's, probably all that we really need to know. In our models, actually, we use 25% pre-symptomatic contagiousness compared to the symptomatic person, just based on some hints and suggestions from other studies that we read, but the other studies that we read, but that's not necessarily a fully well understood property. But clearly this says it should be at least a little bit. So another thing that's important, but there's a lot of conflicting information from different studies, is what percent of COVID infections are asymptomatic. Okay, so again, we just tested a whole bunch of values. So we tested 42.5. Okay, so it's a very specific number there. And that comes from this paper here by Levezzo et al., where they tested an entire city in Italy twice. And found that on average, both times, 42.5% of people who tested positive were in fact asymptomatic. So that's the number that we actually go with in the model. And we kind of see what we might expect, that if 100% of people are asymptomatic, well, on the one hand, you might think that that means that disease doesn't spread as much because asymptomatic people are not as contagious. But if everybody's asymptomatic, everybody is out and about spreading disease for the entire duration of their infection. So that's not good. But as we get down to, these smaller numbers of asymptomatic rates, we see kind of like a little bit of a crossing over of whether it's better to have nobody asymptomatic or maybe a small number of people are asymptomatic. So it's a little bit strange, right? So, I might be able to explain that by saying there is actually a crossover point at which it is better to have at least some people, maybe a reasonable percentage of people, being symptomatic so that they know to stay home and stop spreading their disease. Or it could just be these were, quick, just sensitivity analyses, just 200 simulations. Maybe that's just not enough simulations to elucidate the differences between these scenarios. I could probably explain this in a lot of ways. And that's a bit one of the big challenges of pandemic modeling, is that anything that you see that's strange, you can actually find an explanation to make it make sense, much like a horoscope, okay? Whatever you read, you can find a way to make it make sense for you personally. So that's why you have to be very careful in pandemic modeling about your conclusions and about trying to assess the validity of what you did. Did you make an error in your model somewhere, or underlying assumptions? You have to have a lot of eyes on the problem from different perspectives. So for example, we work with medical doctors, we work with some more classically trained math and stats people in epidemiology, and of course our public health counterparts, to always make sure that what we're doing really does seem to make sense to everybody. Let's see. So we also looked at the probability that a person self-isolates when they have symptoms. So we can see if very few people are doing it, that's bad. But if we can get to at least 80% of people self-isolating, then we're in a pretty good position, and there's not really a huge difference between these outcomes. So we don't really need to nitpick so much about what assumptions we're making in the model about people's likelihood to self-isolate, as long as we are pretty confident that we're in this zone. We also looked at household bubble sizes. So like, your household can bubble with another household. And, we found that even if the bubbles are imperfectly executed, so like if 10% of the households just decide to have way more bubbles than what's allowed, that really actually doesn't make a difference. What really makes a difference is just the bubble size, right? So if everybody has a one bubble, in other words, no bubble, disease just never has a chance to take hold, just doesn't spread. And this is, of course, assuming that people are wearing masks and physically distancing when they're outside. All right, a two bubble, has more spread, but probably still manageable. But then once you have a three bubble, definitely things start to grow quite a bit. And then we looked at how many people does public health need to identify and contact trace to really make a dent in disease spread. So in our model, we assume that everybody who's hospitalized will be identified by public health and be contact traced. So these CT, contact tracing, capture rates are all just outside of hospitalization, so on top of the people who are being contact traced for being in the hospital. So we do kind of see what we would expect, like a bit of a rainbow pattern, where the fewer that are contacted, the worse. And if we can get, so here the number looks like maybe around 50% or better, or maybe you might even say 60% or better, we're in really quite a good position, which is in line with other studies that have come at contact tracing from just a more purely statistical analysis perspective. Although, of course, if you look at this y-axis, all right, these numbers are actually really very small, because contact tracing, super effective at bringing down disease spread. So let's say I just crank up the initial number of infections just to make sure that I'm actually getting a good representation of what's happening. It's not just artifacts of small numbers. And again, we still see the same thing. So in a more directed effort to help understand and guide public health officials in making policies, we specifically looked at the impact of imported cases. So imported cases are travelers coming into the province. So one interesting thing about Newfoundland is that they basically double their population every year with non-resident travelers, with the vast majority of them coming in June to September when the weather is nice. Okay, so we actually have numbers about month to month, what percent of total travel volume is coming that month. We were able to gather information from exit interviews conducted by the Ministry of Tourism quite some time ago, back in 2016, about travel party sizes, as well as why are people traveling to the province. So if people are traveling for work, they get placed into a workplace, depending on where in the province they're actually headed. If they're going to visit friends and family, they get bubbled with somebody, and if they're for some other reason, then they're just there, just them and their travel party, and only having incidental community contacts. So we did this work back in May when Newfoundland's travel ban was first implemented. And if you didn't know, Newfoundland implemented a travel ban in early May, where basically nobody could come back into the province without special exemption. So at that time, it was really not known what percent of travelers would be infected. So we looked at a few different rates of traveler infection. So we'll call them like small, medium, and large rates of traveler infections. And these graphs here at the top are without contact tracing, and down here is with contact tracing. And then we also additionally looked at sort of low, medium, and high compliance with quarantine measures. So anyone who travels was supposed to self-isolate for 14 days. And of course, one can intuit that travelers might be incentivized to not maintain their quarantine, well, because they're there for a fixed duration of time, they've got things to do. So we looked at these numbers, and what we really found is, and it's especially obvious here when the infection rate is high, is that compliance really doesn't matter all that much. Okay, what really matters is just pure numbers. Okay, so what volume of travelers are actually coming in? Because we also didn't know if the borders were to be opened, would there be 100% of the usual travelers? Would it be 50%, maybe 10%? It's just, how many people are going to want to be traveling during the pandemic wasn't known. So we also looked at that. And really just, ultimately, it's just a pure numbers game. All right, compliance is not so important. It's just the numbers of travelers, right? And we can see that, maybe a little bit more clearly when we look down here at these contact tracing numbers, how things separate out a bit more. And then I know I said don't look at the y-axis, but if we look at the y-axis here, between no contact tracing and contact tracing, we said contact tracing is hugely successful at bringing down the number of infections, although even here in the best case, low infections, high compliance, low travel volume, that there is still the beginnings of exponential spread. And these simulations were just for 100 days ending in August. So this is even before school starts. So definitely there are some concerns even here. But all those curves that I just showed you are means with 95% confidence intervals. Okay, they're very pretty. But, all right, one thing that we observed is that most simulations are not average, right? Most simulations aren't somewhere around this mean curve and mostly definitely in this 95% confidence interval. Really not at all, right? So over here, I've got just a plot of just 50 random samples out of the 500 simulations that were used to get, say, this curve. And what we can see is that there are these, small number of essentially nuclear events that take our average and just drag it just straight up. Okay, and if I zoom in a bit, you can see this a bit better. This line here is our mean curve, and all the way down here is most of these simulations. Okay? Most of these simulations just die on out, right? Most of the time, everything is fine. But when it's not fine, it's super bad, and that's what really drags up the average. All right, so much like we've seen around the world, and even here in the GTA recently with outbreaks at Canada Post, at the Amazon warehouse, is that while there is like a slow and steady drip of infections that happens from day to day, there are these big, what I call nuclear events in the model, but these big super spreader events that just catapult everything, and then they make that drip, 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 drip every day a lot faster. So any model that can't capture, the possibility of these nuclear events, is definitely going to probably then be undershooting what might really happen. Because even though these events are kind of rare, with millions of interactions happening every day, these super spreader events are going to inevitably happen. So, 9 times out of 10, you could do something totally irresponsible in your daily life, but one of those times, you might be the cause of something really terrible happening in your community. So maybe not great odds, but definitely makes it difficult to communicate to people the importance of being safe, because most of the times they would be safe. So rather than focus on those mean curves, what we generally like to look at is the probability of certain things happening. So I'm going to show you guys this information as line plots, although generally for public health, I would present this as a bar chart. But what we can look at here is the probability of, let's say, our peak number of active cases exceeding the number on the x-axis. All right. So here we can, I think, better see the relationship of compliance and travel volume for each of the different traveler infection rates. And we can, really see kind of, how bad things can get. Like, if the traveler infection rate is high, like these can't even be on the same scale axis as the others. And then we can look at things like total infections, not just peak active infections, peak hospitalizations, which we feel are probably pretty accurate since they are comorbidity adjusted. All right, and again, here you can really see how just volume is far more important than compliance. And then we can also look at contact tracing daily call load capabilities. And we can see again that Newfoundland at the time had about a 2,000 per day call limit. We can see that if the rate of travelers being infected was high, then there is a very real possibility of exceeding daily call capacity. Whereas for the others, that probability of exceeding is much smaller, although still not nothing if travel volume is high. So the takeaways here, again, we always want to be kind of gentle with our takeaways because, well, it is just a model, regardless of how much goes into it. Contact tracing is very effective, but not enough to stop exponential spread in even the best case travel scenario. Travel volume and infection rates are bigger factors than quarantine compliance, and that the travel ban was likely critically important to prevent COVID spread. So we also looked at school policies. Since we have actual classrooms with actual cohorts, we can actually approximate a real school policy. So in discussions with public health, we asked, well, what would you do if somebody in a particular class is infected? Say, well, it depends. What if there are, 10 people in school that are infected? Well, it depends. And from a real life perspective, that makes perfect sense. But of course, I'm writing a computer program and I need real rules to implement. So we finally settled on this, basic process of what would happen. So anyone who's symptomatic is sent home, not like a workplace where you can choose to be there and people will probably ignore your symptoms. Classroom is sent home if one person is infected. If a school is closed, it's closed for 14 days. And schools are closed if 2 or more cohorts have 2 or more infections. We assume that there's just a general reduction in typical risk just from people being more aware and having general hygiene. We looked at 1 meter desk spacing and intermediate and senior school kids wearing masks. And then since, I've had some observation of people out and about not wearing masks correctly, right? We looked at kids wearing masks perfectly and imperfectly, where we said imperfect mask usage was half as effective as actually wearing a mask. Now, interestingly, one thing that Newfoundland wanted to consider was having kids wear their masks only when they're outside the classroom. And when they're inside, that the 1 meter desk spacing would be enough and they wouldn't have to wear their class. So I actually thought that was kind of ridiculous. But when we put it into the model, what we actually found is that for the most part, wearing the mask either just out of class or all the time was actually fine. Right, that there were enough measures in place, at least without any imports coming in, that it really all came out the same, so that they could take that more relaxed, kid-friendly approach. But as soon as there were even just 2 to 3 travelers escaping their quarantines every month, that we do actually start to see again the hints of exponential spread. Okay. We can look at the probabilities that certain number of schools are closed or certain number of students are affected by school closures. And the takeaway here, again, relatively gentle, is massive any usage in schools, or at least intermediate and senior schools, are effective at reducing cases. If community cases are low, schools have little impact. In other words, schools are probably pretty safe if there's not a lot of infection in the community. But as soon as you have even just a few travelers or anyone bringing in infection in the community, things can really grow. And that can really be set off by schools, right? So you could think of it as schools are kind of like Tinder, right? If there's no sparks around, there's no problem. But as soon as there's a little spark, you could potentially have a wildfire. And then, of course, no model is perfect. As George Box, the famous statistician, famously says, all models are wrong, some models are useful. It's really important to always be very upfront and direct about any limitations or biases that are in the model. And I always have this table front and center whenever I present work to our public health partners, just so that they know what the model is and what it isn't, because ultimately this model is just one piece of information that they use to make decisions, right? It's not the thing that, dictatorially tells them exactly what has to be done. So since you guys are an engineering audience, I'll tell you a little bit about the technical details under the hood that make my model really quite fast. All right, so first among them is to pick a fast and parallelizable language. We execute our parallelization on the high performance computing infrastructure provided by CHIA, the Center for Information and Analytics at Memorial University in St. John's. We've done some complexity analysis as to how the model operates every day. So the biggest thing in the model every day is just figuring out people's exposure. And one reason why most groups can't efficiently implement an ABS is because they actually have to say for every person, loop over every other person to see if they've had contact and does that increase their exposure. So if there are n people, that's n squared operations that has to be done. But what we've determined is that if you sort the population by their health status, which takes n log n time. Then we actually really only have to loop over the susceptible people because they might become infected, and the infected people because they might become recovered or dead, and everyone else you don't even have to touch. It just doesn't matter. All right, so that's actually a huge time savings. And we can actually really take it to the next level by observing that unless we're in some sort of apocalyptic scenario, the number of infected people is going to be far fewer than the number of susceptible people. So rather than loop over the susceptible people to see what their exposure is, we loop over the infected people to see what susceptible people they've had contact with. And we also observed that using nice, easy data structures like vectors is slow. Using very primitive data structures like arrays, super fast. And that when we apply that loop reduction that I just discussed by sorting our population and being smart about how we do our loops, we can really get a lot of speed ups. For contact tracing, we also did some analysis to be really careful about how much memory we allocate and when we allocate it. So we try to pre-allocate memory as much as we can because just the act of reallocating memory is slow. We only even store contacts for individuals who are going to be contact traced if they become infected. So we flip a coin for everybody a priori on that front. And that way we can save a lot of memory by not literally storing the contacts of people who are not going to be traced at all. All we need to do is just make sure that we count up how many people they've had contact with. And then we can clear out memory as we go to save space. And if you're not familiar with parallel programming, generally anything that you run on your own local computer, like this is just on my laptop here in dark blue, is going to be much faster than if you run that same thing in a parallelized environment. However, I can't run 100 simulations simultaneously on my laptop, and that's where you get big speedups. And then we can see how memory increased as we added features into the model. So going from aggregated contacts to exact contacts to adding in contact tracing, basically close to doubled memory requirements. And along the way, we developed, I want to say best practices, but I'm just going to call them practices. Like I said, you have to be really careful about your results and making sure that they're correct. For example, and I'll point this out because this is always good for engineers to think about the process. Very, very early on, we realized that if we plotted all of our simulation outcomes and colored them in order, like simulation 0, simulation 1, simulation 2, we were seeing this disturbing rainbow pattern that should not happen. And it was just due to one number that was not being reset. And so we fix that and we see this, this big, ugly, colorful mess, which is what we expect. And so now when I do my analyses, as I load up every scenario to analyze, I have my code set up so that this figure pops up and I have to manually click through them all to close them so that I'm forced to actually make sure that I'm not seeing any sequential artifacts in the simulations. All right, so in order, you should have some sort of baseline scenario to compare back to. Like I said before, don't just look at those confidence interval plots because most simulations aren't average. You have to determine an appropriate number of simulations to run, which is not always easy either. And like I said before, having lots of eyes with lots of different perspectives is super important. So moving beyond the age-based simulation model, one thing that we did, I'd say 7 or 8 years ago, and that we are redoing now, is taking the contact network that's established by the ABS and then using graph theory applied to that contact network to figure out who are the best people to vaccinate. Okay, so this problem is actually analogous to the critical node detection problem. So we're basically trying to figure out which nodes in a network to remove so that the remaining network is maximally disconnected. And this is actually an incredibly hard problem. It's NP hard, but we previously developed very fast algorithms to get greedy solutions and even approximation algorithms to get us within a known distance of optimality. And then we can look at varying levels of compliance with vaccine directions, and we can find that our algorithms, compared to other network-based approaches, do in fact do a better job at preventing the probability of an outbreak. And then from our solutions, we can back out a series of implementable public policy rules. So this here is just an example that would allow our suggestions to really be implemented in real life. So this year for capstone projects, that's our senior 4th year-long projects, I had one team build an Excel-based tool using design of experiments to see which factors, up to 3-way factors, were most important in controlling disease spread. And each of these factors is some sort of policy lever. And a very interesting finding that they had was that if you pick kind of like a bad policy right off the bat, so if you remember when I showed bubble household sizes of 3, that was really bad. The number of factors that are statistically significant to decrease disease spread is actually really small. So if you're in a really bad position, your options really become much more limited, which is why it's all the more important to always try to keep disease spread low, so you have more levers that you can pull that will be effective. Similarly, I had a team doing machine learning. So they built a user interface where you can input in all the policy levers that are in the model, and we use machine learning to try to predict the outcome, right? And we found that of the 5,000 scenarios that we had, that we built up in our database, that they were falling into mostly 3 clusters of performance. And then the user can see kind of which cluster would a particular policy fall into, and whether it was good or whether it was among the worst policy options. So then that can help public policy officials just circumvent the whole need for simulation and hopefully be able to execute a lot of analysis on their own very rapidly. So in conclusion, right, these simulations, they show the expected results, more or less what we expect to see. But the rocket science in pandemic disease spread is how big are those effects? Those nuclear events that really often kind of define how COVID spreads, they're hard to model, right? Even a model like mine that is more or less designed to behave like real life and to have these events appear, they don't appear all that often, right? So they're really hard to capture, and you have to be careful about how you present and analyze your work to your results to show what's happening there. Like, you can't just look at means and confidence intervals. And anytime you see a model and prediction, you really need to know what was put into that model and what wasn't. So for example, does this model represent any sort of public policy or contact tracing, vaccination rates, et cetera, or not, in order to put those predictions into context. And as with any simulation, anywhere, anytime, ever in the history of simulation, should always take everything with a grain of salt, right? Because this is just a model. It's modeling an incredibly complex situation, largely predicated by people's behaviors, which are random, irrational, and whatever else. So we never want to say that the model says you should do X, therefore you must do X. And if you haven't done X, then you are, a failure, right? As I said before, these models are just one additional piece of evidence for public health officials to consider in coming up with a plan of action for their populations. So I'd like to acknowledge my research team, Benji, Justin, and Yago. So Justin is actually a current second-year student, helped us digest a lot of the information, the data that we needed to use this model. And Yago was a fourth-year computer science student several years ago who helped rewrite the model from the ground up, including doing all that very important loop reduction work. And then also my Newfoundland COVID modeling team, which is led by Proton Raman and Randy Giffen. The end.
Well, thank you very much, Dion. That was a fascinating talk, and I have to admit that as you were talking about the various probabilities and assumptions and things that go into your model, I found myself thinking about how I've been living the last year and where I fit onto your curves. It's I think I'm doing all right, but it was really a really lovely talk to expose us to some of the details of what goes into these models. So it's we have a few minutes before 1 o'clock Toronto time, and we do have already a couple of questions in the Q&A. And so, well, we now have 3. And so I'm going to ask Dionne a few of these. We will finish at 1, and then I will let everyone know that we are heading off into a different app that will allow us to do some networking afterwards. So if we don't get to all the questions, I think Dionne may be willing to answer a few others after 1 o'clock. So why don't we start with a question that came early on. So Frank Bloom, early on you spoke about the reproduction number, and Frank posted a question that said, you referred to it as an average, and the simple question was, wouldn't a median be a better number? And I just wonder if you want us to talk broadly about the use of statistics in interpreting our numbers.
Yeah, so, would a median be a better number than R naught for models based on R naught? The answer is maybe. Kind of depends on whether the mean is, maybe skewed downward by, some people who have almost no contacts, or skewed upwards by people who have very high contacts. The real challenge with R naught is that it's one number, right? It's a sort of like one-stop shopping. Here's a one number to describe a really complex situation. And while it is actually really good at describing just in general, what's the trajectory of disease spread going to be, when it comes to, actually designing a public policy, you need more than just R naught. So even if, you could be able to make the case that a median would be a better tool for R naught to be tied to, it is still just one number.
Very good. I've got a couple of questions that I'm going to combine into one. So an anonymous attendee asked about grocery store and LCBO workers who come in contact with many thousands of people in a year, and are there statistics of how many of those workers became infected? And then Greg Evans of Chemical Engineering and Applied Chemistry, Professor Greg Evans, asked, what is likely to result in a nuclear event? And I wonder if those two questions aren't perhaps related.
Yeah, so definitely in real life, there is absolutely a concern about people who are working in essential or perhaps non-essential but still open industries. Like if you think about grocery store and LCBO, like you hear people talking about like, why can't I just go to the grocery store, this, that, or whatever? Yeah, customers going into the grocery store are going to be relatively safe, but the employees are having, at least some amount of contact with so many of those customers that are coming in. We found, for example, like, then there's what happens like in the back rooms, are they actually wearing their masks or not? Like the Canada Post outbreak in Mississauga was largely due to the fact that the employees were wearing their masks when they were on the floor, like they're supposed to, but as soon as they were in the break room, they're off the clock, they do whatever they want, the masks come off. That's where the problem is. And I absolutely think, because there's no data in Ontario to really robustly support this due to just massive, overwhelming number of cases where our, tragically underfunded and undermanned contact tracing groups can't keep up with. There's no doubt that these workplaces are causing a lot of spread, especially now with the second wave and the third wave even more so. The age groups of the people who are infected are skewing younger and younger to working ages, like 20s to 40s, people who are much more likely to be in these sorts of jobs. But like I said, because of insufficient contact tracing, we really can't know for sure exactly what and how much. And so Professor Evans, that a little bit touches on your question, like, are there commonalities that can be drawn from these nuclear events? Certainly here in Toronto, like the two that I've mentioned, Canada Post to Amazon warehouse, can be directly tied to unsafe working conditions, whether people are actually on the clock or not, and having lots and lots and lots of people in one place. But a nuclear event could be set off by something small. So for example, I think it was Uruguay or Paraguay, almost all of their cases were caused by one socialite attending one party. So, like even though that party only had like 80 people, all right, so that's a lot for like one outbreak, but that just, spread things really quickly. So it is just really hard to know, which is why we all have to be as careful as we can.
I'll ask you the last question in the Q&A, and then I'm just going to close with a couple of remarks. Somebody asked, how did you get involved with Newfoundland and Labrador, and was wondering if you are advising anybody else in Canada with your models.
Yeah, so actually Newfoundland approached me. So that was really cool. Yeah, I mean, Newfoundland, actually they're like a dream to work with. They are so interested in analytical approaches and mathematical models and how they can use data to better inform their decisions. And they have been so fast. Anytime something arises, like they are on it. They don't take kind of like a let's wait and see what might happen with this outbreak before we really try to clamp stuff down and see what happens. So it's been absolutely great working with them. We have provincial support to collect all of the data. So it was great. As for what Ontario is doing, Ontario has their own group of people who are advising them. In fact, actually every province has their own group of people, and I'm part of a Public Health Agency of Canada's external experts modeling group, where all of us who are doing advising to the different provinces meet every week. Well, although of course this year my courses conflict, but we meet every week to talk about what are we doing, what are we finding. But we're just, we're the modelers, right? We're not the ultimate decision makers. And here in Ontario, I'm not in the room when final decisions are made. Just even without knowing about anything that's happening behind the scenes, it is often hard to reconcile the policies or lack thereof that come down with the current case counts.
Well, and of course we'll have more to think about this afternoon. Even I think. Listen, I acknowledge there's a few more questions in the Q&A. I kind of just noticed them; they were kind of off my screen. But I encourage those of you who asked and others to join us right after this. I'm going to have in just a minute. I'm going to have Shannon Osborne come on and post a link. We're going to move over into another app that will allow us to have a more informal conversation. I also want to say that there's another talk that's happening in a week by another member of our Department of Mechanical and Industrial Engineering that I just want to highlight. And I think Shannon is going to put a link into the chat. But Professor Amy Bazelak is going to give a university-wide presentation to alumni on, and I just have to find the title, on electrochemical energy for a sustainable future. And so that's April the 7th. That's a Wednesday evening at 7 p.m. If you have an interest in that topic, the link is in right there in the chat, and you can just click on that and that'll take you to a registration page.